Hi again. Today we're going to tie together a lot of pieces that we've been taking in little chunks throughout the semester up to now. And we had to do that to understand how all these little pieces work, because now we're going to tie them all together and try and explain how it is that the collective cardiovascular system performs regulation. So regulation, homeostasis, all those things we've talked about in general terms before. And even in a couple of specific cases, we're now going to wrap into this big discussion about how the cardiovascular system mostly maintains pressure. But if you think overall, the goal of the cardiovascular system is to deliver blood in a controlled way, enough blood to provide the nutrients, to remove the byproducts, the CO2 that have to be exhaled ultimately. But there's a control system that manages all that makes sure that the flows and the pressures are all where they need to be. So the learning objectives are really to understand how these mechanisms integrate together in a qualitative sense mostly. We'll deal with a couple of equations. There's a homework assignment that will dive more deeply into models that execute some of these different equations and the numerical methods used to implement them in software. And then we're going to explore a couple of different scenarios in which regulation maybe doesn't work, and what happens in our bodies when it doesn't work. And some of that we'll hit in the discussion session. Anchor us back where we've been before. We need to think about a little bit, or review briefly, these notions of cardiovascular, or generally control systems, even outside of the cardiovascular in any system. They arise in physiology everywhere. They arise in engineering, arguably everywhere. And the elements of it are what you see in this diagram. We have to have a regulation system. We have to have some way to turn a dial up or down, or some parameter that we're going to adjust. So you can picture this in our bodies as something like a flow, or a blood pressure, or a heart rate. These are all things that can be controlled. To regulate that, of course, we need a sensor. So the sensor has to detect what the parameter is, what value it has, and then compares that value to a set point. And set points are kind of magic. Our brain has them. It knows what our heart rate should be for a given situation, knows what our body temperature should be, and sets those values. The rest of the system's job is to keep up or down regulating as needed in such a way to keep close to that set point value, whatever parameter is of interest. The comparator then generates a different signal. That different signal goes back to some feedback system which inverts it, hence the negative sign. And there's some gain to that feedback system. That notion of gain is something we'll come back to in this specific context. So it's how powerful that feedback system is able to correct, how quickly it's able to correct, or how powerfully it's able to steer. And of course that can vary depending on the feedback system we're observing. So how does that system now play out in the cardiovascular system? And to frame this a little bit, I'll show you this image. So here we see the distribution of blood flow and the total blood flow through our bodies. Again, they're very approximate numbers. In situations of rest, that's the red bars, and in situations of maximum or high level of exercise. And you see the differences are dramatic in some organs and very stable in other organs. And so you can picture this as being a very challenging situation for the body to respond to. How does the body know, so to speak, and how does it guide that extra blood into the muscles, which are being called upon to perform work in an exercise scenario? How does it, in the context of all that extra blood going to the muscles, make sure that the brain gets enough blood? How does it make sure that the heart gets a little more blood? And how does it sacrifice or shut off the blood to the rest of, or some parts of our body that are not directly involved in the exercise? So that's really the big picture of what we're trying to solve and the way we can solve it. Here's just another image. What happens as we increase the rate of exercise, the demand of exercise, that's measured here on the x-axis in the O2 uptake. So this is the consumption of oxygen, which of course is the main fuel for the ultimate chemical reaction that allows energy to be extracted from the food we eat. So oxygen uptake's a nice metric, a nice easy parameter even in the lab to measure, to tell us how hard we're exercising. And as we move from left to right, we see the cardiac output, which is the Y value, go up, and we see the distribution changes a little bit. Some of these bars or regions of different color, which correspond to different organs. Some of them get thicker, some of them get thinner. We see the skin gets more blood flow to it, for example, during the early parts of exercise. And then toward the later part of exercise, that flow goes down a little bit. So there's all sorts of subtleties in this graph that we don't really have time to get into, but it captures the basic idea that there's an enormously increased general flow through our bodies. Our cardiac output has to go up to pump that flow, and we have to explain how that works, because somehow there's got to be a mechanism, a sensor, some sort of feedback system to make it work. Now, another thing I want to just remind you of is the local regulation. So we're not going to talk about that much because it's happening locally. We're talking about the integrated regulation of the entire cardiovascular system. And when you hear integrated, you can probably guess the brain's going to be involved in some way. But we have a lot of local regulation. And you remember those behaviors, that data that we had to explain in that context, the idea of autoregulation, active hyperemia, and reactive hyperemia. And look back to a previous lecture if you've forgotten a little bit about those details. We also then had long-term regulation at the local scale. So we'll see, as with the local scale, we'll have short-term regulation and long-term regulation. They're all going to be acting over top of each other almost. And as we saw before, long-term regulation is probably going to be the more powerful mechanism, but it's going to be slow. So this we'll see when we now move to the central regulation that we're going to deal with. Now, these are all controls that had to do just with the vasculature. So these were the phenomena we described in the context of the blood vessels, their cross-sectional area, and hence their resistance, which determines the flow given certain pressure conditions. Hopefully that rings a bell or two. Because now we're going to move on to another refresher, hopefully, and that's the way we control the heart itself. So the heart itself has intrinsic control. That's the Frank-Starling mechanism we've talked about, where we see that increased diastolic or end diastolic volume leads to increased contraction and an increased stroke volume. So that we see here in this PV loop, in which we have an increase, a shift to the right of the right-hand edge of that loop. And the two arrows, the blue and the red arrows, show us the stroke volume change. And we see that under conditions of increased preload, that's another term to keep in mind. So increased end diastolic volume is the same as increased preload. If we have increased preload, we move that right-hand curve to the right. When the heart contracts, it may not quite contract as much. It may not be down to the same end systolic volume, but the difference between those two, the width of the curve, the difference between the two vertical lines, is larger, which means we have a larger stroke volume. So we've talked about that. That's intrinsic control. And we've talked a little bit about extrinsic control. So there's another diagram we haven't seen before, but I thought it was a nice summary of all the factors that can determine cardiac output, that can influence cardiac output, because we're going to tap into those when we think about the heart as part of an integrated system. So we see that heart rate is the way that changes cardiac output, and we've talked, and we'll mention again, the cardiac output, the way that cardiac output is regulated, the changes at the level of the cells in the sinoatrial node. We talked about preload, Frank-Starling mechanism. That's something we've seen before. We talked a little bit about afterload, mostly in the discussion. That's a very relevant topic, of course. Cardiac output does depend on the afterload. And we talked about the overall contractility. So how much contraction are the individual cells that make up the tissues capable of executing? That again has to do with calcium, of course. So calcium concentration in the cells will determine contraction and contractility of those cells. So these are all the factors that feed in together to create an overall cardiac output and influence cardiac output. And as I said before, we have described how heart rate is variable and how it's controlled. So we have action potentials from the sinoatrial node, which never are at rest. There's always an upward drift to the membrane potential, drifting up until threshold and then firing the action potential. If we apply a catecholamine, epinephrine, norepinephrine, that increases the current that is responsible for that upward drift, that depolarizing drift, and we get something like this red line, and of course the red line will reach threshold more quickly or earlier in the cycle, and hence bring about an increase in heart rate. And the same is true with another neurotransmitter, acetylcholine, that's typically the parasympathetic system of our autonomic nervous system. That's going to cause not a change in the F current, or that current that's responsible for the spontaneous depolarization. It actually hyperpolarizes the membrane potential. So you see here the purple colored curve. At the end of the action potential, the potential is more negative than it was under control conditions. And of course, if it's starting from a more negative place in potential, it's going to take longer to reach that threshold. And hence the overall rate will go down. So these are all the dials we have to control the heart, for example, control heart rate and contractility. So there's a lot of places that we can control things. So all those things are available to us, and they actually act together. So the heart can be upregulated centrally by means of these neurotransmitters in the autonomic nervous system on top of the intrinsic mechanism. So the Frank-Starling mechanism, which we see in these cardiac function curves on the right, and on the left, these curves of individual muscle twitch tension as we increase the preload. We see on the left-hand side, for example, there's an upper curve that's the total tension. If we apply a neurotransmitter, catecholamine, we increase that curve. We increase the overall contractility of the muscle and shift that curve to the right. On the right-hand side, we see the functional curves, the cardiac function curves, and the Frank-Starling mechanism, where increased pressure brings about increase in cardiac output. Those curves become a family of curves, and they shift sort of up and to the left. So for any left arterial pressure, so that left atrial pressure, that left atrial pressure will tell us how much filling there is in the left side of the heart. And as that goes to the right, as it goes up, then we get the Frank-Starling mechanism. But again, for a given increase or given amount of catecholamines applied, we see more and more work, or more and more cardiac output as a response to that same left atrial mean pressure. So these two effects acting together, the local and the remote. So we kind of know the dials we have, or at least some of the dials we have, vasculature and heart, and now we're going to put them together. And of course, to do that, we need a sensor. We need to explain the sensor. Before that, we have these equations to always keep in mind. These are, of course, the flow version of Ohm's law. This says that the pressure, which in this case is the mean arterial pressure, that is simply the product of the cardiac output and a value called the total peripheral resistance. So this is really nothing more than the hemodynamic version of Ohm's law, where we say pressure is the product of flow times resistance, or in this case, cardiac output, which is the overall flow through the body, multiplied by the total peripheral resistance. Now, of course, these are average values, and this reflects a kind of a steady state, a notion of a steady state. So this mean arterial pressure is not the 120/80, it's actually the mean value of the pressure. So somewhere in between those two values. And picture this equation as describing kind of the overall mean situation. Now this next curve, I really like this graph, more than a single curve, it's many curves. And it really captures the overall regulation of one of the key parameters in the cardiovascular system as a system, and that's the arterial pressure. So that quantity, that mean arterial pressure we just had in the previous equation. And you see here there are a lot of graphs, and we will not go through all of them today. We can be a little more less terrified at this, but there's a couple, and one especially that we will spend some time on. That has to do with this baroreceptor, the curve here in red. That's really the rapid mechanism that is incredibly important for the short-term, quick response to variations in our cardiovascular system. What that means we'll come to in a sec. But what you also see in the x-axis is the time axis in a kind of a funny scale where we go from seconds up to days. And we see that the baroreceptor reflex, typically called, that means of control only works for a certain period of time that's on the order of hours, maybe one day at most. And then you see on the right, the one other curve, we'll talk a little bit about today, a lot more tomorrow, later in the semester when we talk about the kidney. And that's the curve that really starts to climb late in the time course of things, but can climb to infinity. Can climb incredibly high. It's the highest, most powerful regulatory mechanism that exists in our bodies that will determine the response that preserves our arterial pressure. And the y-axis, just to be complete here, the y-axis is is that gain that I talked about a little bit in the context of the feedback mechanism, right? That's the gain of that feedback amplifier. And so this is a metric of how powerful each of these particular feedback mechanisms is. So that's the overall picture, and we'll talk about a couple of the details of a couple of the systems. So again, there's lots more you could dive into. So we remember from the diagram, hopefully, that there was a system, a device, or however you want to picture it, a sensor, something that sensed the value of interest. And since we're here in this domain of pressure, we would like to know where in the body are pressures actually sensed. What's the pressure meter that exists in our bodies? And it turns out there are two different major places in the cardiovascular system where that occurs. And that's what you see in this anatomical rendering here. And you see these red dots, they are the aortic bodies, they're called here, and next to them, sort of in fine lines, you have to look more closely to see those, there are the baroreceptor fibers. And these are in the aortic arch. So on the left, you see a picture here of the aorta, and it goes up and goes down. There's a couple of vessels that go off the top. They become the carotids. And on the right, you see a picture of one of those carotids, a little bit further up, where the carotids branch. So at the branch point of that carotid artery, you also see nestled in there, the carotid sinus is what this is called, and nestled in there you also have carotid bodies, and around those, these baroreceptors. Okay, so what's a baroreceptor? It should be sort of obvious from the name, arguably. Baro is pressure, receptors as a receptor or a measurement system. So these are devices, not devices, they're tissues, they're cells, they're nerves, they're parts of our nervous system that respond to mechanical stretch by changing the rate of action potentials that they generate. Like most things in our nervous system, the means of control and communication is the rate of firing of the action potentials. And just like our eyes see light and our hearing apparatus works, the pressure sensor apparatus that exists in our hearts or in our arteries, these are based on stretch changes that bring about changes in the rate of firing of the action potentials. And this graph shows what I mean. So this is the mean arterial pressure. This is kind of a weird graph. So on the top, you see the pulse pressure. That's the blue tracing. And then on the bottom axis, you see time. So it's obviously a repeating pulse over time. And the different traces correspond to different levels of mean arterial pressure. So this is when we're at 50, which is a perfectly reasonable, a little low mean arterial pressure. 75, you can imagine, is a little more typical mean arterial pressure. Once we get up to 100, 125, and certainly 200, we're at abnormally high mean pressure levels. So, and as we go down in the curve, or this set of curves, there's more and more pressure. And with the higher pressure, we see a consistent and heavier and more rapid firing rate of these action potentials. So the encoding of the pressure information is in the frequency or the counts of the action potentials that are coming from these baroreceptor. And what we also see is a very rapid rate of frequency of pulses during the rising phase. So if you look at the pulse pressure, as the pressure jumps up, we see the highest density or the highest frequency of those action potentials in these sensors. And then as the pressure decreases, it decreases more slowly. And as it's decreasing slowly, and even when it's at its peak already, the rate is starting to decline. So even when that pressure is still quite high, the rate's starting to decline. And then as the pressure decreases, the firing rate declines even more sharply. It goes back down to zero in some cases for a while before it picks up quickly. And this is consistent with what we know about baroreceptors. This is another way to capture this behavior of the baroreceptor response. So here we have the discharge frequency on the y-axis, and on the x-axis we have the pressure. So as pressure increases, the rate of frequency firing goes up, and that's what we see in these graphs. But there are two graphs. One is the immediate response to a sudden change in pressure, and the second is the response 45 seconds later. So you can imagine applying a pulse of pressure, stretching these baroreceptors to a fixed amount, and you get a big jump in the firing rate. And then if you just hold it at that pressure for a while, in this case 45 seconds, you'll see that the rates all go down. So the firing rates decrease quite dramatically. They get as high, in some cases, as high as 30. These are pulses per second, so 30 hertz is the frequency there on the left-hand side, and they all end up down about 8 hertz. And they're all sort of clumped together in much lower frequencies. There's still an increase, there's still a rise over the resting condition with that higher pressure, but not nearly as dramatic. So this is really how these fibers respond to changes in pressure quite dramatically, more dramatically than the absolute value of pressure. They arguably respond to both, right? They go up when the absolute pressure goes up, but they go up more dramatically when that pressure rises rapidly. And so this is a behavior that they have. So now we have, I think, all the makings to put together a kind of a picture in our mind of the process that happens when we have a change in the pressure of our system. So the scenario to picture is you do something in the body, something about the body changes to cause an adjustment in the pressure that is existing in the aorta. And so you can picture this as we jump up off a couch, or we lose blood, we've got an accident, or we have a response in our brain. There's this thing we'll talk about called a vasovagal response. So all these effects that alter our arterial pressure temporarily will hopefully be restored through this baroreceptor reflex. Now it's reflex, which means it has multiple steps going on. So here's a picture. This is called a map of the response of the baroreceptor reflex to changes in the signals, in the pressure in those areas. So what we're seeing here is the carotid sinus and the aortic arch. They're the two locations where the baroreceptors sit. And the idea here is that there's an increase in the pressure, and that pressure will then transmit that information to the brain. And the brain then activates a cardiac decelerator. So this is a little bit strange, right? So this is cardiac. This is something that will slow down the heart rate. And you also see something that will, if it's positive, that's the left-hand side. So if there's an increase, a cardiac decelerator. If we have a decrease in pressure, then the pathway goes to the right and activates the cardiac accelerator and also the vasoconstrictor. Because remember, anything that increases cardiac output or total peripheral resistance will cause an increase in the pressure. So restore the pressure back to normal values. So on the left-hand side, you see response of a deceleration. On the right-hand side, you see an acceleration of the heart and a vasoconstriction. And then you see, so that's the response at the heart level. So the medulla is talking to this accelerator, and this accelerator is sending information through the autonomic nervous system to, on the left-hand side, you see this impulse going to the sinoatrial node that can regulate the frequency up or down. That's why there are two arrows going into the sinoatrial node. In the case of deceleration, it's a negative influence, and so it slows the heart down. And that right-hand blue arrow, that's an accelerator. That's an upregulation of the frequency of the heart. And then the right-hand side, you also see, and you remember that when we had stimulation through the sympathetic arm of the autonomic nervous system, this is the release of the catecholamines, and we got an increase in contractility. And so both of those effects are acting at the heart. On the right-hand side, we see the effect on the blood vessels themselves. And here we have an increase in stimulation of vasoconstrictor stimulation, which causes a constriction, slight or more depending on the degree, constriction on both the arterial and the venous side of the vascular system. And all of these things are working in tandem and ultimately bringing about a restoration of the pressure. So here's another map. So there's another way to see this. So again, hopefully, one or more, hopefully they'll all make sense to you eventually, but hopefully one of them initially is kind of clearer to you. You can start with that. Here we have increase in blood pressure. So this is a specific case of an increase in blood pressure, and then that causes an increase in the firing rate of the baroreceptors that we just talked about. That information goes to the cardiovascular control system in a part of the brain called the medulla, and it goes to that part of the brain and decides what to do, okay? And it decides what to do in two ways. So this is a little more complicated in the sense that it says it causes a downregulation of any sympathetic stimulation that might be happening at the point where the pressure goes up, and it causes an upregulation of the parasympathetic. And that now feeds in this slightly more complex picture where we have from left to right the arteriolar smooth muscle, so that causes either vasoconstriction or dilation depending on the stimulation. So if we have down regulation of sympathetic stimulation, then that's a down regulation of that smooth muscle, which will cause vasodilation, which you see right below that. That's the alpha receptor. You can also have stimulation or downregulation of the stimulation of the sympathetic system going to the beta-1 receptors. And we know the beta-1 receptors change at the heart level, the ventricular myocardium, that cause a change in the force of contraction. So that can cause a decrease in the force of contraction in this particular case. On the far right-hand side, we see the effect on heart rate. So those arrows also feed in. So we have a down regulation of the sympathetic stimulation, an up regulation of the parasympathetic stimulation. Both those actions are causing a decrease in the heart rate. And so the heart rate goes down. We see that effect. The decrease in force of contraction and the decrease in heart rate, both of those contribute to a decrease in cardiac output. Similarly, over on the vascular side, we had vasodilation, so that's going to cause a decrease in peripheral resistance. So everything is downregulated. Both products on the right-hand side of that equation are downregulated, right? Cardiac output, total peripheral resistance, and the result is that the pressure goes down. So an increase in pressure initially is brought about by a decrease in pressure when all these regulation systems start to act. And then there's a part of our system that is feeding back in the sense that blood pressure decrease is sensed by those same baroreceptors, and now their firing rate will go back down. So where it was elevated to start this whole chain reaction, now that firing rate will go back down because the pressure has been decreased. So this is the way to picture this. Very simple system, right? Very simple, very trivial system. Here's yet another diagram showing the changes in the peripheral resistance and how they affect the total peripheral resistance. So we have these arterioles, we have these resistance vessels, we have individual control of those. This is yet another version of the same thing. I think there's enough text here. If you're interested, you can read your way through this, but the bottom line is the same thing, that if we get an increase in the mean arterial pressure, then we ultimately, through this regulatory system, see a decrease in cardiac output and a decrease in the total peripheral resistance that ultimately results in a reduction in the pressure. And this can go both ways. So there's all kinds of room to move here, to regulate both elements up and down and really refine the level of control that we get out of it. So that's the system. That's there are a couple of others we could talk about, but they have similar overall patterns in the sense that they have this sensor, they have a set point, they have a way to regulate through those same channels of the autonomic nervous system. And at the end of the day, we have many systems, as you saw in that original diagram, many systems overlapping that can regulate the overall pressure. So let's now talk about a specific case of where this system might be upset, might be disturbed from its homeostatic equilibrium contentment. And that's the situation of hemorrhage, leading potentially to shock. So hemorrhage is when we have a sudden loss of blood, right? We all know that. That loss of blood, if it's small, of course, we've all cut ourselves doing some things, more or less silly. The small loss of blood, we don't even notice. The vasculature heals itself, seals itself. We don't really lose that much blood. But if we're unfortunate enough to be in a major car accident or for some other reason lose a great deal of blood, then there can be a number of systems that will kick in to try and restore that blood pressure because the body carefully monitors that blood pressure, as we've seen. And we can see that sometimes those compensatory mechanisms work and everything is fine and the blood pressure stays up even as we're losing blood volume. In other cases, it won't. And this graph, which is from an older textbook by an author named Guyton, and this book shows as a function of time the arterial pressure response in the case of hemorrhagic blood loss, so sudden blood loss. And each one of the curves corresponds to a different amount of blood loss. So the first one is a small blood loss, and we see the pressure goes down for a little bit, and then it pretty quickly comes back up to normal values within, let's say an hour, right? So these are often responses that take minutes to really operate. But it also takes minutes for blood loss to happen typically. So if we lose a little more blood, we get case 2. Lose a little more blood, we get case 3. But in all cases, the pressure at least is mostly restored, if not fully restored. It's really only case 1 that gets close to full restoration, and they're all stable. They're a little decreased, but they're still stable. And that's compatible with sort of more or less normal life. Maybe not with exercise, but at least the subject, patient, whatever, will be alive here. Now, in case 4, we see something different. In case 4, we see an initial compensation, so restoration of pressure up to a certainly reduced, but certain level, and it sort of wavers around and continues well out into several hours. I mean, 180 minutes, 3 hours, almost getting to 4 hours, and then suddenly the pressure drops. That is not because additional blood was lost. That is because the mechanisms, the regulatory mechanisms that we have in our bodies were not capable of maintaining that blood pressure. At some point, their time ran out for a number of reasons, and so the pressure dropped. And we see in case 5 that same sort of behavior where initial restoration, but even earlier, because there was more blood loss in 5 than in 4, even earlier, the blood pressure really drops quite precipitously. And in case 6, the blood pressure never really even comes close to a useful restoration. So you see the maximum restoration goes back to, see too, the pressure at the end of the blood loss is down around 15 millimeters, or actually that's percent, so 15%, and it goes up, maybe gets up to 40% of what it was, and then loses control again and completely, goes to 0 at something like 3 hours in. So this is kind of fascinating. I mean, how does this work? Why does it only work to a certain extent? We know something about it, but not everything about it. What we can also capture in a case like this are these so-called function curves. So again, function curves, I've showed you those before. That's the Frank-Starling mechanism, basically, where we have increased, if you see in the x-axis, right atrial pressure, so that's a measure of the preload, and then cardiac output, that's the y-axis. So we increase preload, we expect the cardiac output to go up. And what we see at 0 time is a perfectly healthy Frank-Starling curve. Pressure increases, cardiac output goes up to a certain maximum value, but that's a healthy response. But as time goes on, for the different times after a single hemorrhage case, a non-compensated hemorrhage case, then we see the actual function of the heart decreases. So the heart, the pump that's needed to maintain this pressure, this is the only source of pressure increase in our system, that function decreases with time in the face of an uncompensated hemorrhage. And as you can see, this can take a long time to play out. This can take hours to play out, which is why with cases of blood loss, we do have a window where the system will try and restore the blood pressure. But if nothing else happens, if that blood isn't restored, or at least liquids, IV fluids aren't restored, and the blood volume decreases and stays low, then hours later, the patient can decompensate, and we use this word medically, can decompensate and actually die. So this is a system we really need to understand in lots of scenarios you can imagine, of accidents, obviously in war and battlefield injuries. There's lots lots of motivation to understand this. So here's a picture that we see of the baroreceptor reflex. So as the pressure drops, in the case of a hemorrhage, we get a decrease in pressure causing a decrease in stress on the carotid sinus baroreceptors, a decrease in the firing rate. And that then causes 2 responses again. It causes a downregulation of the parasympathetic, that's what's on the left-hand side, and that, as we know, regulates heart rate, overwhelming, that's its most important role. And the right-hand side, we see an increase in sympathetic stimulation. And of course, now we know that causes an increase in heart rate, increase in contractility, causes a vasoconstriction of the arterioles, all of which, and even a constriction of the veins, all of which is to try and restore that pressure, right? So it's increasing the cardiac output multiplied by the total peripheral resistance in order to maintain that pressure. And that's the response. And again, the baroreceptors play a big role in that. They drive this. They're the sensors that really drive it. Now, there's lots of other things that go on when you start to lose blood, or when the blood pressure drops as a function of blood loss. So on a sort of compensatory side, we get the baroreceptor reflex, right? It, as we saw, tries to restore the pressure. One of the other curves that I didn't talk about also kicks in at this point, and that is when the brain doesn't get enough blood. So when the brain doesn't get blood, it's called cerebral ischemia, then lots of alarms go off. The brain starts sending massive signals to the cardiovascular system to restore that blood pressure. And that also helps. So you can imagine even a stronger sympathetic response that would cause even more heart rate increases, more contractility increases, more vasoconstriction to try and restore that lost blood pressure. There are also chemoreceptor responses. We haven't even talked about that. There's a whole system that's distributed throughout the body that measures the concentration of certain substances in our blood. And those are called chemoreceptors, obviously enough, and they will also add to the vasoconstriction in a way because, again, they sense an abnormal composition of the blood in such a way that restores the pressure by increasing local vasoconstriction. We also get reabsorption of fluid from the tissues. So you remember we talked before about how there's careful water balance between the blood and the extracellular or the interstitial spaces outside the vasculature. And in these situations of hemorrhagic loss, that balance shifts away from the background norm, which, if you remember, is a slight leaking of water out of the vascular system, turns the other way around because the pressure in the blood vessels is decreased. So already the hydrostatic pressure is decreased. So the water will tend to be pulled from the interstitial spaces back into the vessels to restore that blood volume. And so we get all kinds of responses. The last one that, again, we'll mention briefly, we'll get back to, this is the one that involves the kidney. There's a whole hormonal chain here. It's called the vasopressor renin-angiotensin system. Nice short name. So we'll get that. But the net result of that is, again, massive and substantial vasoconstriction. So all things that will restore the blood pressure. Now, all that you think would be a pretty good insurance system. Multiple layers to bring back the pressure to what it needs to be. Unfortunately, when things go too far, we tip over a point at which many of these mechanisms are no longer adequate and in fact may even contribute to a decompensation. So one of the things that happens when blood pressure goes down is less blood flows to the heart. And if less blood flows to the heart, then the heart becomes ischemic. The heart suffers from blood loss. And if that's the case, then its cardiac output goes down. So it could be being massively stimulated by the sympathetic arm of the autonomic nervous system. But if there's not enough blood getting to that heart, it can't respond by increasing contractility. And so the cardiac output will actually go down, which of course is a bad thing. Another thing that happens for a number of these reasons related to ischemia and metabolic changes is we get acidosis. So an decrease in pH, increase in the concentration of hydrogen ions. And that leads to a compromised vasoconstriction. So the smooth muscle that vasoconstricts won't maintain that vasoconstriction in the face of acidic conditions. And so they relax. Even though they're being massively stimulated by the central nervous system, they relax because of the acid that's present in the muscles themselves and the tissues around it. We also said the brain gets ischemic and causes a massive release. If the brain doesn't get enough blood, if that reduction in pressure causes an ongoing reduction in the brain blood flow, then we get central nervous system depression. So instead of this massive alarm bell going off, the brain starts essentially to shut down and go to sleep and stop functioning. And then we can even have this a weird sort of effect where we can get blood clotting that starts to rise because the blood isn't flowing very much, it's static, stationary, and then we can get, that can cause all kinds of initially good things, sometimes bad things. It's a very mixed response to that. But the bottom line is that when it happens in the brain, it further increases the ischemia. When it happens in the heart, it further increases the ischemia. And both those are bad things, are not productive things, they're decompensatory elements that cause a reduction in the overall response to this attack. And so this is, in a nutshell, again, there are many more details why we see this initial attempt at restoration of blood pressure, restoration, in the situation of hemorrhage that is sometimes effective, but sometimes not, and it can take minutes to hours for that to play out. So it's very interesting to think about this control system playing out over many different timescales and involving many different systems, all of which are capable, under the right conditions, of restoring the pressure. But if pushed beyond those limits, cause it actually to get worse. They don't just stop helping, they can begin to hurt. And so this is why that drop in pressure can be so precipitous. So when the system gives up, so to speak, then the pressure drops quite dramatically and quickly, and that can cause a very rapid death. Another story that we can only partially tell, but is one to start sort of tickling your curiosity with, is what happens at altitude. Because at altitude, we also get compromise to the cardiovascular system because of the decrease in the oxygen pressure. So the hydrostatic or air pressure decreases at altitude, and that leads then to ultimately less oxygen getting into our bodies, and we get a situation of hypoxia. And that is also a compromised situation that our brain senses, that causes an increase in sympathetic response and a systemic vasoconstriction. And we'll see there's some, cardiac vasodilation. There's all kinds of things. It's a complicated story, but you see a lot of involves the respiratory system. That's why I won't tell this whole story until we know a little bit more about how the respiratory system works and how it regulates. Because as we see, the cardiovascular system contains all these various elements, and they all have to work together in order for us to maintain that homeostatic situation that keeps us alive and keeps our nutrients arriving, our oxygen arriving, our byproducts removed, and keeps us happy and healthy. So that's brief look into it. I think it covers most of what's in the textbook, plus a couple of other interesting, hopefully, little sidelines. This is a deep topic, as you can imagine, but that should give you enough in a specific context of the cardiovascular system. But try and place it in this global context of saying that all of physiology ultimately has examples of this. All of physiology has control systems, and they've evolved to the point where as long as they're functioning normally, they are all set or able to restore a homeostatic state, to bring us back to that homeostasis that we strive for, and that we crave, and in which we continue to live, and we continue to be a functioning organism. So that general notion of a sensor and a comparator and a negative feedback, that we'll see in any physiological system. So whenever you're asked or get curious about a control system in the body, just think of that picture and say, okay, where's my sensor? Where's my set point? How does this work? How does the communication happen? And then eventually you'll at least know all the right questions. And then with those, you should be able to hopefully find the answers you need, as much as we know them, about the control of that particular system. So that's a dive into the cardiovascular regulation system. Hope it was interesting, useful, and augmented what you're reading in the textbook. And thanks so much for your attention. We'll see you soon.